to the presentation that we'll have from Omer and Mazen today. So over the last few months, they worked really hard and was working with me and Kwame. And and their final project is seismic phases classification. So yeah, today they'll do the final presentation, and afterwards we will following up with that, we'll present their certificates. So Omer, please go ahead. And this is basically work me and Kwame did some time ago. So Kwame was the main person who did all these projects. So he will ask questions at the end of this project, like end of the presentation, and then we can conclude. Yeah. Thanks. Omer, go ahead, please.
Thank you, Dr. Tanisha, for this kind introduction. My name is Omar Ashraf, and my partner today is Mazen Hassan. Today I'll be presenting our project on AI-powered facies classification under the guidance of Dr. Tanisha and Dr. Kramer. This project leverages machine learning to classify geological facies from seismic data. It's a critical task in energy explanation, so let's dive into the details. Mazen will follow up from starting the slide. Please, Mazen.
Hello everyone. Thank you,
Hi,
Omar.
Mazen.
So basically, our workflow followed 5 key steps. The first step was downloading the dataset. Second step was configuring and augmenting the data. The third step was designing neural network architecture. And the fourth step was training and hyperparameter tuning. And for the final step was deploying the model via Flask web app. Okay. So for downloading the dataset, we downloaded the Deutsch F3 dataset from the link provided in the task description. After that, we extracted the files and saved it. And the data is now ready for loading and splitting. For the data configuration and augmentation process, we followed a 3-step process. The first step was loading the labels.mpy files for patch-based splitting. After that, for the splitting process, we created inline and cross-line patches for training and validation. Then split the dataset for relative splits, 80% for training and 20% for validation. After that, we started our augmentation process. We augmented the data using Python scripts that was introduced to us. The aim of this approach was to decrease overfitting and class imbalance. Data augmentation was only applied to the training set, including techniques like rotation and flipping. The data was then shuffled to ensure the model doesn't memorize the order of samples. Additionally, we created data loaders for both the training and validation sets, which efficiently fed the data into the model during training and evaluation. This step was crucial for maintaining a smooth workflow and ensuring the model generalized well to unseen data. And now I will discuss the neural network architecture we are using for our seismic data segmentation task. Our primary model is UNet, and we are leveraging pre-trained models like ResNet34 and ResNet50 and Inception v3 in the UNet encoder for future extraction. UNet is a powerful encoder-decoder network with skip connections. The encoder extracts feature from the seismic data, while the skip connection preserves spatial details, making it highly effective for segmentation tasks. This architecture is particularly suited for our needs due to its ability to handle detailed feature extraction and spatial accuracy. And to enhance the feature extraction process, we use pre-trained models in the UNet encoder. Here is why we chose ResNet34, ResNet50, and Inception v3. We chose ResNet34 because it's a lightweight model, making it ideal for moderate-sized datasets, and it's also pre-trained on large dataset. It can be fine-tuned on seismic data to adapt its specific patterns. And for the ResNet50, we use it because it offers more complex feature extraction capabilities. It provides a balance between depth and computational efficiency. And like ResNet34, it's pre-trained and can be fine-tuned for seismic data. And for the Inception v3, it's known for its efficiency in feature extraction through its unique Inception modules and it reduces computational cost while maintaining high accuracy. And its pre-trained nature allows for effective transfer learning on seismic data. By integrating these pre-trained models into the unit encoder, we leverage the restraints in future extraction. These combinations allow us to achieve accurate and efficient segmentation of seismic data tailored to our specific requirements. And for the next step, it was a hyperparametric tuning, and Omar will start from here.
Mm-hmm.
Thank you, Mazen, for your presentation. To optimize performance, we tuned hyperparameters like batch size, learning rates, and occasionally dropout rates or dropout layers. For Resident 34 and Inception V3, we used a random search strategy to explore combinations. Uh, uh, the our parameters explored were all the same for all models, with the batch size being 16, 32, and 64. Our learning rates were 0.01, 0.001, and 1/8 to the power negative 4. We explored a grid search in Resin 34 since it was our first model, so we tried a systematic approach, but later on we tried a random search strategy. And for Resonance 50, we explored the dropout layers, which we'll explain later on why, and a weight decay of 1.1 e to the power negative 5, which we only tried once because it gave us uh, accurate results for us. Optimal findings and challenges. Our optimal findings, which we later on used as our training parameters, were all the same with a batch size of 64 and a learning rate of 1/8 to the power negative 4. As I mentioned before, we had some challenges with Resin 50 due to its high validation and the training losses due to overfitting. We tried experimenting with the dropout layers. However, it provided little to no improvement. So you opted with introducing L2 regularization and weight decay into a cross-entropy loss function, which helped reduce overfitting and increase our accuracy. So that's why we opted with weight decay. Testing strategy. Our test strategy, we evaluated the models on two test sets,
Mm-hmm.
and on each set once only, and then we took the average of these accuracies and we set it as our overall accuracy for the model. Um, we Resident 34 achieved a 93.5% average accuracy. It was fast, but less than the other models. Resident 50 reached 96.7%. However, it used the most computational resources out of all the models that we used or we tested.
Is this
Inception V
testing or the validation accuracy? Like
testing.
testing, okay.
Yeah.
Okay, got it. Mm-hmm.
Inception V3 delivered the best performance with an average accuracy of 97.2%. It balanced speed and precision, making Inception V3 our top choice for this project.
Mm-hmm.
The Flask web app. To make our models accessible, we created and built a Flask web app with three key pages: a home page, a models page, and a documentation page. How did we
Mm-hmm.
do that? We took the best model.pth files and integrated it into the backend of our app. We created a responsive yet intuitive interface, which lets the user choose a model, and then the model would then segment the image and display its results. The content of the app, it has, as I said before, a homepage, a models page. The homepage lets the user introduces the user to the tool and links to the documentation. The models lets the user pick a model, upload the what type of images, and then view the results. The documentation provides a detailed technical workflow and model specs, and makes the user, if the user wants to learn more about how we train the model and the process. These are images of the homepage and the documentation page. In summary, we pre-processed the Dutch FT dataset with augmentation to combat imbalance. We tested multiple architectures with Inception achieving the highest average accuracy, deployed the solution via an intuitive Flask app, and then this project demonstrates how AI can streamline seismic interpretation, saving time and resources in energy exploration. Thank you for your attention. we'd be happy to take any questions.
Thanks, Omar, Mazen. It was a very nice presentation. So my first question is, do you have your app handy? Like, did you record your app? Like, did a screen recording? I would
Oh,
be interested
my app.
to.
I have an app. I have an app here.
Okay, yeah, sure. Can you please
Yeah, so,
demonstrate that? Yeah.
okay, so this is the home page. It has like a hero section, which with two main buttons, trying the
Mm-hmm.
model or learn more, and then
Yeah.
just for public sake, we have meet the team section, and then the
Mm-hmm.
footer. When we kind of click the try the model and it goes into the model page,
Mm-hmm.
which has, as I mentioned before, three cards. We can select a model and then upload an image, and then it will
Analyze. Okay. So can
provide the
you
results.
upload an image and let's check that? Maybe.
Okay, it's just any screenshot here.
Can you upload a real image? Maybe. Do you
Uh,
have it?
I don't have any seismic
Uh,
image. I
okay.
apologize for that, but
Okay.
we can try later on, and then I could provide results later on.
Sure.
But then
Mm-hmm.
then it should display results, and then two buttons where the user can download a PDF report. We start over and
Mm.
select a different model.
Yeah.
And
Okay.
then the documentation page has technical documentation regarding all the models that we used, um, such as how many layers, how many parameters, input size, learning rates, and weight decay for resonant 50, and the optimizer of choice. Just
Mm-hmm.
what we explained in the presentation, just it's all in the documentation section for users' sake if they want to learn more. So yeah,
Okay. Okay.
that's the
Yeah,
Great.
I'm sorry to interrupt. I have some test images for uh, for the model. If you want to use it.
please, yeah, please,
Yeah.
Mazen, if you
Sure.
can send
Yeah.
it, share
Maybe.
it with
Yeah.
me.
Mhm.
Okay, just a second.
Kwame, do you have any questions?
Yeah, I do have a question, but let's first see the demo and then I can ask the question.
Okay.
Okay, Mazen,
Yeah, Omar, I send you two
yeah,
different images.
yeah. And here's the image, yes. And I'm going to select, for example, the Inception V3.
Mm-hmm.
And so the downloads, test slice, it's just analyze. So it will take it's a segmentation model, so it will take the we programmed it such that it will only display the dominant facies. And here, for this in this case, it's the lower North Sea. We can
Okay.
download a PDF report and sorry,
Okay. Let's see the PDF report. Maybe.
yes. This PDF report will just say it's generated on in this date, the model used, dominant
Okay.
facies, and the full analysis.
Okay. Got it.
We can start over, try a different model. I think Mazen sent me another image. Oh, sorry. Sorry for the mess and the hassle.
It's okay.
It's sending failed. Okay. Send. Okay. So we're trying resonance 50 with a different slice.
Mm-hmm.
Analyze. Again, the most dominant faces the lower North Sea.
Yeah.
So
Yeah, that's so you do know that there were quite a like different or in the group or class
yeah,
imbalance problem, right? There was
yeah,
a
there
very
was
few. Yeah.
yeah, there was such a large class imbalance.
Yeah.
So,
So that's mostly, I think this is the one that was mostly represented. Two or three classes that's more represented in this.
yeah, that's one of the key points that we tried fixing, but we couldn't because there's such a large gap between classes, and
Mm-hmm.
we tried the different augmentation oversampling or even undersampling, but that didn't work. So we just mo tried just moved on. We didn't try to fix it. We said it is what it is.
Yeah.
Okay.
Okay, I think
Yeah.
Kwame can ask now. Yeah.
Yes. So nice presentation, nice UI as well. I just
Yeah.
have like two, three questions. First of all, can you please clarify? You mentioned that this is a segmentation model. So right now here, I don't see any segmentation map or basically segmentation of the facies from the seismic image.
Yeah. Okay, this was
So
something we programmed. What we had before in the previous versions of this web app, we had a version where it had all the segmentations. As we can see here
mm,
in the report, it provides a whole entire full analysis. But we tried for user experience. We outputted only the dominant facies.
okay, okay.
But in fact, it is a it is a segmentation model. That's why
Then
if we tried the different image, it would give a different report with the entire segmentation
Can you show
samples.
him the? Can you download the PDF report for this image? Yeah, show him.
So as you can see, it's entire analysis.
yeah, but ideally, what we would have wanted to see is a map basically showing where this North Sea land is present, where this Ridgeland chalk is present, and where this Zixtine is present. I
Yeah.
mean, is this a classification model or a segmentation model? And if
I
this is a
think it's
segmentation,
a segmentation. No, the
Yeah,
code they
it
use
is.
here is a segmentation code
if
from it.
if this is a
Yeah.
segmentation model, if this is a segmentation model, then ResNet is basically a classification model. So how are you guys doing
No,
segmentation from?
ResNet, it's a ResNet backbone.
Okay, and then what
And
is
ResNet,
the
yeah.
decoder? What is the decoder part?
The
So
unit.
UNet with the ResNet backbone, I think, right? Can clarify that? Yeah.
Yeah, can you show you the code,
No,
or
no,
can
no,
I
no. You
show
don't
you
have.
the
If you
notebook
can just
so I can
explain.
explain it more? Yeah. So basically, we're using unit, right? For because
Hmm,
it's a segmentation model. Yeah.
hmm, hmm,
So we for the coder we are using like ResNet or Reception or any other models that extract just
hmm.
spatial features and the features about the image and every pixel about it. And for the decoder, it classifies every pixel.
Okay. 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 Then just one last question. So here, as you mentioned that this is a class imbalance problem, and it's essentially a multi classification model.
Yeah.
There are multiple classes. So you have done an analysis and showed the evaluation metrics for basically accuracy only. But since it's a multi-class classification model or segmentation model, it would be better like if you analyze each class separately. Then what is the
Yeah,
accuracy
yeah,
of
we
each
have this
class?
information, but it's in the code.
Okay.
It's in the code, but we have all the information. Yeah, we have every for every class how many pixels is correct, how many pixels is
Mhm.
incorrect, and the accuracy of each class in a
So
specific
perhaps
batch. Yeah, we have this information.
yeah, yeah, just a suggestion that I mean maybe include all these things in the presentation. But that's it. That's it from my side.
Yeah, okay. I understand.
So it's
If you want us to show you the code,
No,
we
that's
will
all
show
right.
it.
I
No, that's all right.
actually
This is just a
just
suggestion.
yeah, it's a suggestion. I think there's a it's a very good way that you guys presented. It was a difficult assignment. I would suggest if you want to work on it, Mazen and Omer, then you can try including. So I think when you actually looked into your training set, you already had it or already provided you with the segments, right? So the code I provided to you for generating these samples would have also created these segments. Okay. So that's what, because of course you guys are not geologists too, because it's a geological problem statement. You would like to see how all these, but it's also true for any segmentation problem though. But you'd like to see where are these locations, where is the region line, okay? So for if you want to improve on this, then keep adding these things to your code. Okay, that's only the
Yeah, so
suggestion.
basically you're asking us like to create an image but with a colored pixels for the
Yes.
Yes.
classes, yeah? Yeah,
Mm-hmm.
yeah.
Yes.
Yes.
As
Yes.
like we are visualizing the images. Yeah, I
Right.
understand. Yeah, yeah.
Yeah.
We didn't add this feature actually.
That's okay. That's okay. We liked your UI, and there's a lot of scope to improve this UI. And so I will. I also shared the paper. I think in the beginning of the class, what which Kwame and I wrote. So that's what we also did, is show where the locations are. But this is good. This is good enough. So thanks all, and let me just because we are recording. Thanks for your hard work, and I will email you your certificate just to show it in the recording also. Just a minute. So
should I
this
stop
is
sharing?
I'm also already sharing. So
Okay.
yeah,
Okay.
so this is for I think Mazin. Just make sure that I will when I email you, make sure that your name is correct, and this is Omer. Okay, so it's first of
Yeah.
February, and big, huge congrats to both of you for working so hard so far.
Thank you.
Okay, and I definitely, we all wish you definitely to be more deep learning experts. And yeah, nice. I mean, I really enjoyed those sessions, the Sunday sessions, and hope you carry on with this deep learning enthusiasm.
Thank you all for the
Thank you.
experience and knowledge you guys have passed on. I really appreciate the past few months, and as you said, the Sunday sessions, they were really knowledgeable and full of information, and I really enjoyed them. So thank you
Thank
again.
you. Thank you. Thanks.
Thank you.
Okay.
Thank you. Bye.
Okay.
Bye
Then
bye.
bye for now. We'll